Alright everybody, this will be the last video lesson I give for this chapter, which will be phase diagrams. The last lesson is just going to be like a quick vocabulary rundown, everything we talked about, and a quick worksheet after that. But there won't be any more video lessons for this chapter. And then we'll have a test April 15th. Biggest thing though is to make sure that when you guys do the assignment for this lesson, make sure you look on Google Classroom and on the e-lesson plans because it's going to be a modification of two worksheets put together from problems from both. So make sure you understand which one you're doing from. All right, let's move on. All right, so phase diagrams. So these are similar to the phase change diagrams that we talked about before, which remember those outlined if here's your chart, here's your x-axis, which is your energy, and this was temperature, right? They look something like this. Well, now a phase change diagram is actually going to be looking at not only how temperature can affect the state of the substance, but now also how pressure can affect it too, right? So you have something like a substance like in a piston, and you have a heat source underneath it, and you have it at a constant pressure, at a different temperature, you take some readings, and you see how that actually now affects how the temperature and the pressure dependence will affect how the substance will phase will be in. And what we'll call this is a phase diagram, right? So what a phase diagram would look like is, so we're going to draw one out first. All right, so let's say, draw a pretty big one. Oh, I should do a line. Here we go. Here we go. Oh, I have to buy it. That's crazy. Whatever. We'll go with my crude drawing. Okay, not bad. So what's going to look like is you're going to have on the y-axis, you're going to usually have pressure. In some usually like unit, let's just use millimeters of mercury in this case. Okay. And then on the y-axis, that's where you'll have temperature. Okay. So let's say we're going to look at the phase diagram for water. Okay. Let's call this spot 760 millimeters of mercury. So 1 atmosphere, normal atmospheric pressure. Let's call this 0 degrees Celsius. So these will all be in Celsius. And let's call this about 100 degrees Celsius. So how it's going to look is you're going to have three basic lines in this graph. The first one you're going to have is this line starting from a low pressure and a low temperature. Okay. The second line you're going to have usually is one going upwards, in this case, sort of like that, and then another curve going this way. So what's going on here is you're going to have three basic regions in this phase diagram, okay? You're going to have a solid, liquid, and a gas region. So in this case, for water, remember this is for H2O, okay? This is going to be your solid part. Do a different color. This will be the solid. Up here is going to be your liquid phase, and down here is going to be your gas phase. And now what this tells you, if this is the phase diagram for water, this will tell you at what temperature and what pressure what phase water will be in. So for example, like if we were at negative 20 degrees Celsius, which is maybe right here, and you're like at 700 millimeters of mercury right here, you'll be at the solid state of water. Let's say if you're like at 1 millimeter of mercury, so a very low pressure, you'll be in the gas phase of water. Okay. So if you look at it, each one of these lines actually symbolizes a phase change going on because that's where they separate between each of the phases. So if you look at, let's do green, this first one, this line right here, between the solid and the gas phase, okay? That means everything that lies on this line is going through a phase change like those plateaus were. So like if you remember the phase change diagram, that plateau was a phase change happening. This line is the exact same equivalent. So this line is a phase change happening, which this is what we'll call the sublimation curve. Which, remember, that means now that we are going from, in this case, we're subliming. So we're going from a solid to a gas. So we're basically going this way with the phase transition. Right. The next line we're going to look at is the one between the solid and liquid, okay? Which that's going to be your fusion curve. Remember, for fusion, that was when you're basically melting. So that's what's going from essentially the solid to the liquid phase. And this last one is going to be your vaporization curve. So that's when you're going from the liquid to the gas phase, remember. So that's what each one of them states, is that this is where the phase change is occurring. So that's, remember, when the substance is in both of those phases. So remember, if you're on this fusion line, this fusion curve, right, if you're exactly on it, it's between a solid and liquid state, remember, okay? Now, we're going to talk about two other critical points in this diagram, for example. The first point that we're going to talk about is the one that meets right here, okay? Which, if you look at it, it's where all three lines meet, so that's what we'll actually call the triple point. And what this states, the triple point, okay, if you're meeting, all those lines are meeting at one single spot, that means those are the unique set of conditions that allows this substance to be in all three of those states at one time in equilibrium. So that means at this specific temperature, at this specific pressure, I can have H2O existing as a solid, liquid, and a gas at the same time. That's what the triple point means. The last point that we'll talk about on this curve is basically where the vaporization line ends, because it does actually end. Okay? And this is called the critical point. And what the critical point means is this represents the temperature and the pressure above which a supercritical fluid exists. So what that means is once I get past this critical point in a substance, okay, everything above it, so like let's say like this area over here, let me erase this diagram over here real quick, is what we'll call a supercritical fluid. Okay. And what a supercritical fluid basically is, it's sort of like not a state of matter. It's like where something kind of exists, but it's not necessarily like one of the four states of matter that we kind of talked about. But usually some phase diagrams have a critical point at which above that temperature and pressure, a supercritical fluid will exist now. Okay. So let's see what else I want to have. So I talk about the phase changes. So this will tell you all of that stuff. I got the critical point. All right, so that's that one. So let's look at a phase diagram real quick for, let's say, a different one. Okay, let's look at not H2O. Real quick, one thing I want to talk about before we erase this one. Notice this slope of the fusion curve real quick. That's a negative slope, right? Because it's going in a negative direction. And notice how the pressure this is at 760 compared to the next one that we're going to do. So let's erase this one. And let's look at, let's say, CO2, carbon dioxide, and how that compares to water. So here's your pressure again, in millimeters of mercury. Here's your temperature in Celsius again. Okay. Now let's look at how the one for carbon dioxide exists. So first off, carbon dioxide's triple point actually exists at, oh, I want to use ATMs actually for pressure, my bad. Exists at 5.1, and it's at about negative 55 degrees Celsius, about. So that's where the triple point of carbon dioxide's at. So far I got, whoops, that was a bad line. Let's redo that. Go in there, okay? And then it still has its sublimation curve, okay, or vaporization curve. Remember, this was the sublimation curve, this was the fusion curve. But now it's, sorry, it's vaporization curve, but now its fusion curve is going to occur a little bit differently compared to water. It's actually going to go up. Okay? And it does have a critical point. So it has a point right there too, which that's at actually, for reference, like 31 degrees Celsius and like 70, this is not drawn to scale, 73 atmospheres. But if you notice this, first off, carbon dioxide has a positive slope here, which is actually what most molecules will go through. Water is an atypical, has an atypical fusion phase diagram, which has a negative slope, but this one's a positive slope here, which is what you want to occur. But if you look at CO2, actually, the really weird part is how its solid state over here, here's its liquid state, here's its gas phase, right? We know CO2 mostly exists as a gas, right, in our normal basic environment, right? We go outside, we actually kind of experience CO2. But if you look at where 1 atmosphere is, about right here, which is our normal pressure, right? And normally we're going to actually have our normal temperature, which is approximately over here, right? So if you notice, if we actually put out dry ice, and what dry ice is basically CO2 as a solid. So it's like ice, but it's just CO2 molecules instead of H2O. If I'm over here, if I have dry ice, let's say I put it out on a countertop right here, okay, it's going to automatically go to a gas because we're at a temperature over here, right? So if you look at it, CO2 is something that will actually undergo sublimation to get to where it wants to be at the temperature, right, which is like approximately over here. So if you ever actually put dry ice, if you've ever seen dry ice, you put it on a table, automatically you see vapors coming right out of it because at our specific pressure and at the temperature we're at, it doesn't want to be a solid. So it'll automatically sublime to a gas to be where it wants to be. So this will also tell you what will actually happen if you put like a liquid portion of CO2 at a specific temperature and pressure. Like if it's over here you want to get to, it'll vaporize very quickly. So this will tell you what the molecule will actually undergo when you have a specific set of conditions. All right, let's review real quick then everything before we end. This one went a little bit longer, but that's okay. Hopefully you're still with me. So some terms real quick, okay? If we ever talk about equilibrium, that's the substance that is in between two states. So like it's going in between a solid and a liquid. Because remember, this is where the phase change happens. So you generally see this during phase changes. Triple point, remember, was the set of conditions which all three states are equally stable and in equilibrium, remember. Critical point was the set of temperature and pressure in which a supercritical fluid exists. And remember, what that supercritical fluid is a substance where it isn't distinctly a liquid in a gas phase, but it doesn't really exist, right? It can effuse through solids like a gas, but it also dissolves materials like a liquid. So it's a really interesting type of thing. But it's not actually one of our 4 phases, remember, that we talked about way back when. Okay? Because it doesn't actually exist really in nature. All right, one last thing I just want to show you guys before we end, so you guys have it for your reference, is just a quick phase change diagram, a more accurate one of how water looks. So here's how water looks, basically. I'll leave it up for you guys. You can pause it if you need to. But remember to look at the specific assignment for what problems you have to do for phase diagrams. If you have questions, like always, let me know.